Okay, I think we're on.
Okay, so today I'm taking a stab at talking more about things related to art and reciprocity and classification of torsors over number fields and stuff like that. And but I'm trying a slightly different approach today, and it's sort of a retreat. It's sort of a retreat in the spirit of John Conway's instruction to, I guess it's his redoing of Poya's idea, that this idea of, I don't know, induction on problems or something like that. So what was it Poya said? If there's a problem that you can't solve, then there's an easier problem that you can solve. But that wasn't quite a mathematical induction thing. So Conway turned it into, if there's one you can't solve, then there's an easier one that you can't solve. This is the optimistic hope that there's no infinite descent. You don't run into.
Well, then if there's no infinite descent, then that statement is wrong. I think if there's a problem.
Well, no, the instruction is to try to do that, and it'll ground out at some point. So maybe I didn't say it right, but
yep. Yep, I'm in love with this approach, in fact. Yeah.
Okay. So so in this case, what's the harder problem that maybe I can't solve and the easier problem that maybe I can solve? Well, and it's not completely clear about, to what extent I can or can't quite solve these problems. But so the harder problem in any case is, well, to make it specific, let's say classifying all the Z mod 3 torsors, perhaps over any algebraic variety, or perhaps over any algebraic stack, but in particular over any number field, over, if you want to say, over the spectrum of number field or something like that. And perhaps I should also say over any number ring or something like that. But and it's not so much that I can't solve that problem. It's that to the extent that I have a solution, it seems rather unwieldy, so unwieldy that it's hard for me to describe it to you. So, I've sort of been trying to, I sort of feel like I have a solution to this problem, but it's unwieldy to the point where I've been, spending a lot of time trying to tell you this solution. And it's kind of, Rube Goldbergish, Heath. What is it, Keith Robinson? That's where you are, Keith Robinson?
I don't know.
Okay. Where are you? Are you in UK?
In Scotland, in Edinburgh.
Okay. And right, so the hard problem is classifying the torsors over the number fields, roughly speaking. And the easier problem is classifying the Z mod 3 torsors. I did say Z mod 3 torsors. This is just an example, but classifying the Z mod 3 torsors over the finite fields. So it's really just number fields versus finite fields. And I mean, in a way, the classification over the finite fields is trivial in a way, but it's not that trivial. It's there's something slightly non-trivial about it, and that slightly non-trivial thing in the classification of the Z mod 3 torsors over the finite fields is supposed to be the sort of local thing that we're going to sort of globalize to get the nicely organized classification of the Z mod 3 torsors over the number fields. So I'm not sure I'm saying, I said local and globalized. I'm not sure exactly, but I'm not sure exactly how how various people talk about this kind of thing. But it's kind of, the vague idea is a number field partakes of a lot of little finite fields. Not exactly homomorphisms, but there's something like a homomorphism. So the big idea is that you can try to take a number field, sort of take it apart into its little local finite fields. Again, maybe people don't think of it as finite fields. Maybe people think of it as local fields or something like that. But that's the way I'm thinking of it for a moment. We're sort of going to take apart a number field, analyze a number field into finite fields. Well, we're going to sort of take that for granted, but we're going to try to use that as an approach towards analyzing the classification of Z mod 3 towards its over number field. So we're going to sort of try to reduce it in this sort of local way. And of course, I've been doing this all along, but I've been doing it in a sort of sloppy, unconscious way, not noticing that, not noticing that if we really try to clarify the finite case first, then the hope is that the number field case won't look so unwieldy. So that's the plan. That's the organization plan.
Okay.
So, and of course, we're going to, do this in very ad hoc ways and personalized ways based on some personal history between you and me, talking about various things. Like we used to talk about Zeta types. Do you know what I mean by Zeta type at the moment? A sort of categorified, or perhaps groupoidified, or something like that version of a Zeta function.
Yeah.
Right, and I guess, right, so sometimes we would talk about, a Zeta structure type, but we'd also occasionally talk about Zeta stuff types. For example, when you were groupoidifying certain numbers related to pi, we actually did get into some stuff types as opposed to structure types. So, going up the hierarchy of property, structure, stuff. And I think we're going to have something like this again. So what am I trying to say here? So, yeah, so we're gonna start thinking about things like Zeta series and L series, and sort of their combinatorial and categorified and groupoidified background, and we're going to think about applying this, utilizing this in our problem. But first, we're going to talk about some of the whole idea of Zeta series and L series and their conceptual nature. And who knows to what extent we'll get distracted into talking all about that before we even get to the problem that we asked.
I paused the recording. No, I didn't pause the recording. I tried to pause it. My computer.
Are you trying again? You're still waiting for? Well, what's going on? Should I wait?
You should keep on going, I guess, because it decided not to pause it.
Okay. So right. Okay. Right. So that's the idea. Zeta series and L series, but possibly from some very idiosyncratic, fancy conceptual ways that seem conceptual to me, and possibly to you. But anyway, so let's jump into it and try to remind ourselves of various naive and possibly less naive ideas about Zeta series and stuff like that. So let's take a let's start out imagining that we have like a commutative ring, for example. Okay. So let's say so hopefully my tablet screen is visible now. So like A is going to be a commutative ring. And we have the idea of the spectrum of that commutative ring. In other words, you could say the geometric interpretation of that commutative ring. And there's actually probably multiple different meanings that people give to the concept of spectrum of a commutative ring. But they're all, they all fit together roughly, I think. And they're all this idea of giving the geometric interpretation to the algebra. And as usual, this geometric interpretation is contravariant compared to the algebra. And, so that idea of the spectrum means homming this commutative ring A into some other standard commutative rings, perhaps some special fields, or, depending on how you think of it, you can think of it as homming it into all other rings. That's what's a very special class of rings. It's not a class of special rings, but it's a special class of rings.
It's even a proper class.
What? Say it again?
It's even a class. It's a class.
I guess it is, yeah. A proper one, yes. Right, so the idea of a zeta series or a zeta type or a zeta thing is really related to the idea of a spectrum of a community. It's kind of a little partial snapshot of the spectrum of the commutative ring. It's really just kind of like a little partial snapshot that involves just homming the commutative ring into finite fields. Roughly speaking, right?
Well, say exactly what it is.
Okay. So there's all sorts of different ways of doing this here, and I may get ourselves horribly mixed up by forgetting to distinguish between minor different variations of the idea. But so let's say, for example, let's say, don't tell me, let me think. So yeah, so let me describe something called the zeta type of A. So this is a structure type. Well, so in again, I don't keep very up to date on how people talk about these things, but like Joyal's structure types are types of structure carried by finite sets. We can think of this. This zeta type is really, in some sense, going to be a structure type that's carried by finite fields. But you can, interpret that as a structure type that's actually carried by finite sets, because you can think of finite field as a type of structure that's carried by finite sets. So you can kind of compose in that way, in some sense. So, so let's say, let's say to start with that there's this structure type carried by finite fields, and that's what I'll mean by the zeta type of A for now. And so suppose that F is a finite field, and there's that much special about F being finite at this point. We're just treating it as a field, but the finiteness restriction is what's involved in the zeta type. Don't tell me. So what am I trying to say? So we say yeah, okay. So I don't know. I'll call this I'll notate it like that for the moment. And so I want to say that a Z sub A structure on F is a it is a homomorphism from A to F. So I mean, it's very straightforward.
Yep.
And how is that a structure type? Well, because it's a type of structure that can be carried by finite fields, and in particular, we can transport it along isomorphisms of finite fields.
Mm-hmm.
And yeah, so then there's this, like I said, we're going to sort of compose structure types here. So there's this Riemann zeta type, which is the structure type for finite fields, finite field structures. No, I didn't quite get that correctly, did I? Let me think. Okay. So maybe I should call this, is there a name for this is going to be like the logarithm of the Riemann zeta thing. I think. We'll see if that works out. There's some famous name for that thing.
Is this a structure type on finite fields or on finite sets? This one.
This is going to be on finite sets.
Yep. Okay, that's what I thought. I don't know a name for the logarithm of the zeta function.
Koblitz talks about it a lot. He must have a name for it.
The logarithm of the zeta function. I don't know. Does it have some other name? I don't know.
I wouldn't be surprised if he calls it the zeta function.
Oh yeah. I mean, for people of a more, I don't know Koblitz, but if for people of more people working on the Baez hypotheses might call that logarithm thing the zeta function.
Yeah, because they might, or something like that. Yeah. Okay. Yeah, I'll believe you about that. The structure type for finite field structures on finite sets. So, all right, yeah, I have to think about this for a moment. I mean, right. I mean, for you and me, this should not be so bad, but for anybody trying to listen in, this could seem very idiosyncratic. But it's really not that bad. I mean, I don't know. I can imagine you wanting to provide some pattern at some point, but let me keep on going a bit here. Maybe I should say R sub L here, that it's the Riemann zeta type in logarithmic form or something like that. We're being very ad hoc here on notation and stuff. So, yeah, this is an example of a structure type that fits into Joyal's theory of structure types, except that in French they called it species of structure or something like that.
Yeah.
And those are kind of what categorified Maclaurin series or something like that. Or Maclaurin series is sort of a semi-fancy name for power series or something like that. So let's try to identify this specifically as a let's try to identify this specifically as, concretely as at the level of Maclaurin series.
Okay.
So, are you going to tell me the answer right away, or do I have to sort of struggle?
No, I'm not, because I haven't thought about it too much, but I'm really,
Okay. Okay. So this. All right. So, first of all, let's try to get a sense for which coefficients are going to be non-trivial.
Okay, the prime ones.
Prime power ones?
Prime power ones. Yep, sorry.
Okay. And prime power ones. And the prime power ones. Is that already? I'm hoping that's already going to make you optimistic about this working out to be the logarithm of the Riemann zeta function or something like that. Because remember, right, one of the tricks is, that these are categorified Maclaurin series, but we're actually treating them as right. There's a sort of there's that Fourier transform for the multiplicative group or whatever. What's that called? The
Mellon transform?
Mellon transform. Yeah, the Mellon transform. And the Mellon transform is this thing that in some strange way converts between Maclaurin series and Dirichlet series. I guess that's one of the reasons I like calling them Maclaurin series, because then I have two people that this Mellon transform is connecting. So there's now this Mellon transform, right, works in some sort of high-powered analytic way, but it does, right, it turns out to have sometimes some very concrete series interpretation, right? I mean, it's not quite correct to say I'll say the incorrect thing, that's too coarse, but it's in some sense only slightly too coarse, because you just have to figure out how to make it more correct. But right, roughly the idea is you've got a function that, first of all, I can't remember which one is the Mellon transform and which one is the inverse Mellon transform. Maybe you'll be able to figure that out for me, or maybe not. But but they connect the Maclaurin series and the Dirichlet series, and just by taking the same series of coefficients and reinterpreting as the different kind of series. So let's write down what these series look like in a naive algebraic way. So a Maclaurin series looks like I don't know, something like F. Well, I don't know. I'll call it G for the moment, unless you tell me to use some other letter. G of, let's see, maybe it's traditional sometimes to talk about X, or is it Z? Let's see, I'm not sure. G of X equals some sum of coefficients times powers of, so it's the sum. And again, there's all sorts of issues about how do you deal with these infinite sums and things like that. Do you use analysis? Do you use some sort of magic category theory, et cetera, et cetera, et cetera. but the sum over J of some series of coefficients. So I don't know, maybe I'll call it A sub J. So that's like a Maclaurin series. And again, you're allowed to complain, comment, and suggest improvements here. And now if you just take the same series of coefficients and think of it as the coefficients of a Dirichlet series, then what does that look like? That looks like, maybe I'll call it G bar of X equals the sum over J of, don't tell me, so maybe it's something like J to the power of negative S or something like that?
Yep. Except you should stick an S on the left side if you like that letter.
Okay. And okay. Just looking for the eraser here. Yeah, I'm not at all sure I do like any of these letters. And I can't remember how much anybody else likes these letters or what they like. But the rough tendency here is that X is going to want to, often it's going to want to range over some disk, some right?
Uh-huh.
I mean, in some cases it could be an infinite radius disk, but that's a little bit unusual. Is that right? And on the other hand, the variable S, what does that want to range over? That wants to range over.
That wants to range over a right half plane.
A right half plane.
The numbers whose real part is big will make that tend to converge.
Okay. So yeah, that's has something to do with the theory of Dirichlet series, the analytic theory of Dirichlet series.
Yep. I'm amazed that you're talking about any of these analytic aspects at all. I'm curious to see why.
Well, it's for cultural reasons, but I did actually, well, okay, I'll tell you one reason why. Because like I said, this is not, it's not quite accurate to say that that the relationship between this Maclaurin series and this Dirichlet series, it's not, I mean, there's an awful lot of fine print involved in explaining how this graphic algebraic process corresponds to Mellin transform. I mean, there's all sorts of convergence issues, of course, but there's also, but that's not the main glitch. Do you know what the main glitch is? I wish I could remember what the main glitch is. Yeah.
No, what? I don't know. No, I don't know what you're talking
about. So what am I trying to say? It's like there's an extra term or an extra factor or something that shows up.
Oh.
It's like the zeroth. Don't trust me on this. Well, but part of the point is that I actually, I really wanted to learn some of this stuff, and even though it was in analytic form, which I'm usually allergic to, I felt like I had to actually try to learn some of the analysis in order to deal with some of the serious glitches in how Mellin transform works. So it's I mean, what am I trying to say? It's something like, so let's see. Don't tell me. Let me think here. What are we saying? Yeah, I think it must have something to do with the zeroth term, right? So Dirichlet series are sort of allergic to having a zeroth term. Is that right? Or do they? How does that work?
Yeah.
J, what is the index J
That starts at 1.
That starts at 1. I mean, you could try to start it earlier, but that's not exactly the way people usually think.
No.
But for Maclaurin series, the index J really wants to start at 0.
But we're not interested in fields with 0 elements.
Yes, we are.
That's even worse than the one field with 1 element.
Is it? Let's see. Let me think. Let me think about what you're saying. No, didn't you get it wrong? Let's see. What am I trying to say? Fields with 0 elements, fields with 1 element. Let's see. Okay, now maybe you're right. Let me think. But there's going to be something. Well, there is going to be something about some very low term here or something like that. Very low index term. I thought it was going to be the 0 index, but maybe it's going to be the 1 index.
Are you talking about how like the zeta function gets mixed in with a gamma function when you're trying to do good stuff with the zeta function?
I'm not sure.
Gamma function is connected to the real prime. That's the way they usually put it.
That might be what's going on. But I just want to emphasize that you can take a really naive approach to Mellin-Disk transform and just say that it is this naive algebraic process. And and you can try to do that in the categorified picture or the group productified picture or the categorified picture as well, right? You can talk about
we've done that. We have a little paper about our stuff that's sitting on the NLab about at that level of sophistication, and I'm perfectly happy with sticking at that level of sophistication unless there's like some reward to be reaped.
Well, I mean, okay, so there very well may be, and it may come into the story at some very interesting points. But my excuse for bringing it up now was mainly to respond to your comment or question about your shock at my almost talking about some of these things as though they were analytic objects.
Yep.
So for the moment we're not going to worry about it. We are going to take this very naive approach to Mellin transform at the moment, but with the proviso that there may actually be some very interesting stuff going on with and that may be amenable to categorification, reportification, etc. That involves taking a less naive approach to Mellin transform and thinking about these. Again, I think one way to you said something about gamma function, but there's also something has to do with some very low value of j equals 0 or j equals 1 or something like that. I'm not remembering how that works. And exactly because I was getting mixed up between between what you said, finite, there are finite fields of cardinality 1, but there aren't real. Well, actually, there aren't, but there are all. You can pretend that there are. It's much harder to pretend that there are finite fields of
cardinality 0.
Cardinality is 0, but there are other things. So I don't know, but okay, yeah.
Well, anyway,
that's all. That's possible fun and games for later. But let's try to proceed for now. Right. So one of the approaches, right. So in the sort of naive but categorified or group productified approach that you and I have taken in that paper that you referenced, one thing that we do is we take, Joyal's structure types And we do, we consider the same thing that Joyal considered, which is we consider this Maclaurin convolution, categorified Maclaurin convolution on these structure types. But we also consider this categorified Dirichlet convolution on these structure types. And we consider it we consider it to be when we talk about Mellin transform, we talk about it in a very informal way, and it's just kind of talking about the idea that we're shifting interest from Maclaurin convolution to Dirichlet convolution or back. And what did you say something else?
Yeah, saying sure. Let's go ahead. I want to get some.
Well, okay. So okay, so we can take, am I saying this right? We can take the exponential. Let's see. So what kind of exponential do I want to take it? So we've got the structure type for finite fields.
Yeah, in our paper, we take the exponential of that. You take the exponential of G.
Yeah, but you take the Dirichlet exponential of that? Am I saying that right? Yeah, the Dirichlet exponential of that.
Yeah. So I guess, yeah, the exponential of G bar is the easiest way to think about it. And then that's the Dirichlet series for finite semi-simple rings for the structure type of finite semi-simple rings, commutative semi-simple rings. Yeah.
Right now, remember when we since we didn't know what we were doing at that point, and maybe we still don't know what we're doing, but particularly since we didn't know at that point, we just kind of didn't know any better, so we called these things semi-simple rings. But before we called them semi-simple rings, we did think about whether they should be called, whether there's some way to use the word separable in there. And at the time, it seemed like that wasn't quite the right word. It wasn't quite the right word, and still not quite the right word, I think. But still, right? Then we've learned a lot about separable things since then.
I mean, well, one thing is that like a finite, let's see, well, an algebra, a finite dimensional algebra over a finite field is separable if and only if it's semi-simple. So we don't.
But then, can you explain? Can you? But my question is, can you explain why? When I suggested that we call them separable back then, you said no. Somebody said it's the wrong thing to do, and we had to call them semi-simple instead. And I think you were right when you said that, but I just can't remember exactly.
I don't remember.
Yeah.
I don't remember that. Now I know more about separable algebras, and so I know the distinction. Well, I mean, so now you're talking about separable rings. So I know I was just now talking about separable algebras over fields, and then I know that.
Right. The problem is the problem is that it's right. We can't just say separable algebra. We could what do we say? Separable algebras over. Yeah, we can say semi-simple rings, but if we start saying separable algebras, we have to start saying separable algebras over something, and then it's tricky to figure out what to say it's over or something like that. But maybe you're right. If we work one prime at a time or something, then maybe we could do that. I don't know. I
don't think it's worth worrying about this yet. I think you're trying to get to something interesting.
Well, but
you're talking about all these sort of nitpicky annoying issues that are worth sorting out once you got to something interesting.
Well, but there is a point to this. Let's see. So what are we saying? We're saying x of RL, maybe say the Dirichlet x of R sub L is equal to the Riemann zeta type. The Riemann zeta type. And so I mean, so right, one of the things we're saying here is that you can take structure types in Joyal's sense. So I'll just call that structure types. But you can take the slice category over the Riemann zeta type. And right, so that is, that's, structure types carried by finite fields. No, structure type, yeah, well, let's see.
Well, if you use RL, then it'll be over finite fields.
Yes, I'll do that. Okay. Structure types over RL equals structure types over finite fields. And well, I mean, it is true that there's some things, some of these things you're complaining about might going slow here. There's some things that I want to say just very briefly. And they're going to be important, but I can see why you might think that, well, actually it would be better to get to the concrete stuff here. But I'm just going to try and say a little bit about it anyway. So what am I trying to say? That so this so this is a Grothendieck topos. And so as a Grothendieck topos, it's a theory. And you can think about what this is the theory of. And it's interesting to think about what it's the theory of. And perhaps, and you could do it like for all primes at the same time, the way we would set up right now, but perhaps we could, focus on just one prime or something like that. So we would have structure types over finite fields of characteristic P. Right. And okay. And yeah, I just want to say some of this, even if we're not really going to use it today, but it's really going to be eventually, hopefully, important and interesting. So there's this thing Lovier talks about the double negation topology on a topos. And you can do that in this case. So okay, so again, let me try to write down more specifically that we're doing this for a specific prime P. So P is a prime, ordinary classical prime, like maybe 5 or something like that. And yeah, you were asking why I didn't pick 2 or 3. What?
No, I was saying 57, which was Grothendieck's favorite prime.
Yes.
Okay.
And You don't feel obligated to point out you don't want to.
No.
What's the word I'm looking for? Wasn't that what they killed Socrates for misleading the youth or something like that?
Take my chances.
Okay. So let's take structured types. I think that's right. Over say, I hope I'm saying this right. R L, I guess I'll put a comma or something like that. P. And so I guess that's like an Euler summand. Right? You talk about Euler factors of Dirichlet series, but if you're
so
if you're looking at the logarithms, then it's really an Euler summand instead of an Euler factor. Yeah.
Okay, but it's the structure type on finite sets of being a field of characteristic P.
Yes.
Okay.
That's right. That's right. And so let's call that Grothendieck topos T. And yeah, so what is this the theory of in the geometric doctrine? And I don't know. I mean, it's something like it's not quite correct, I think, to say that it's the theory of a finite field of characteristic P. But if we take the double negation topology of this, so I don't know, Lovier tends to notate it that way or something. I don't know. I think this is easier to describe what it's what this is the theory of in the geometric doctrine. So this is, yeah, and boy, there's an awful lot of claims and details and things here that really need to be checked. I hope I'm not totally screwing everything up beyond the point of repair. The double negation Grothendieck topology on this topos gives us a new Grothendieck topos. And this is the geometric, as a theory in the geometric doctrine, it's the geometric theory. I'm not sure whether I haven't told you this already. I know I've told Todd.
I don't remember it, so I'm waiting.
Yeah. It's the geometric theory of algebraic completions. Sorry. Is that the right word? Algebraic completions, closures. Do you have a preference? I remember Toby Bartles insisted that one of them was correct and one of them was incorrect. And
people say closures. I started running around saying completions, and people said, "What?" And I don't know how I picked up that habit, but it was probably
well, you got it from me, presumably. But yeah, I still think I prefer complete or something like that. But the geometric theory of algebraic closures of FP. Which you can also think of as being the geometric theory of torsors the whatever that's called, the absolute Galois group of F sub P, or I don't know, some étale homotopy group or something like that. The geometric theory of torsors of the, I'll call it the absolute Galois group of F sub P. So it's like the automorphism group of the closure of, well, that's a very tendentious the there, right? When you talk about the algebraic closure of F sub P.
Right.
And that's the whole point, that it's so tendentious. It's so tendentious that there is this group that you get, and it's actually a profinite group. But it's like, the profinite automorphism group of, it's like aut of, this notation that pretends that there's a the algebraic closure. So it's like the automorphisms, I was going to say over F sub P. You don't really have to say over F sub P because it doesn't have any automorphism. And again, you have to think about some reason why this is a profinite group. But it is, and it's basically, again, I don't know the right way to say this, but it's like, you want to say that it's like profinitely generated by the Frobenius or something like that. Freely profinitely generated by the Frobenius, if that makes sense. You know what I mean? Is it like a profinite, some sort of profinite completion of Z or something like that?
There is a profinite completion of the additive. Wait, what is this? The additive Z? Yeah, the additive Z.
The additive Z, yeah.
Yeah, there's a famous group like that.
And I'm hoping that is the absolute Galois group of any of these finite fields.
That sounds right to me. What is the name of that profinite completion of Z? Maybe that's just what it's called. It's a famous. I mean, there's stuff you can say about it pretty easily. But anyway, I'm forgetting my stuff.
Well, but I'm hoping that this is really close to being correct. This is not irreparable. This can be fixed up to be correct. And
I don't have any sense for why. Well, I was about to say I don't have any sense for why the double negation topology of T would have this effect. Then I'm suddenly remembering that whatever it is, it'll be a Boolean topos, this double negation thing, and Boolean topoi. Well,
yeah,
categories of actions of groups are.
Yeah, you're on the right track. Yeah, go ahead.
So at least we're heading in the right direction. But I don't know why you get this particular. I mean, I don't know why you get this particular group.
Well, there's such
great many other groups.
There's such great examples like this. For what am I trying to say? It's like
maybe it's
right. There's like variations on the theme of genericness here. What am I trying to say? Different meanings of genericness. Generic point of a. Let's see. What am I trying to say? All right. What am I trying to say? That. All right, okay, let me try to give you the ridiculously oversimplified philosophy of double negation topologies, okay?
Okay.
And the whole interesting story to tell about this, how it relates to, Cohen's forcing, or actually Solvay, and who's it? Solvay, and who's the other guy? Dana, Scott and Solvay. Scott and Solvay I don't really know the history, but I got the impression that they reinterpreted Paul Cohen's forcing method in terms of, the stuff that wasn't horrible to people who hate analysis. Because Paul Cohen was an analyst, right? And he actually thought in terms of probability theory and stuff like that. So it's, Scott and Salovey, I think it was them who, really figured out a way of thinking about Paul Cohen's forcing method in a way that was much more attractive to people who hate analysis. And then Lovier, reinterpreted the Scott Salovey thing even more so in terms of Grothendieck's theory of Grothendieck toposes and stuff like that. And not just Grothendieck toposes, but other toposes. But relatively Grothendieck toposes. So I mean, whatever Cohen was doing, he wanted to say something like, we want to create a model, like a model of set theory where some bizarre thing happens, like the continuum hypothesis gets violated or something like that. And he wanted to do it by sort of starting by pretending to make a little bit piecemeal progress in a certain way. Just it was too hard to construct a model all at once, so he would just sort of describe certain ways to improve the model, correct certain defects, but it had this whole, you had to the goal was somehow to correct all the defects at once in some sense.
Yeah.
But it was really hard to describe how to do that because correcting one defect could introduce other defects or something like that. But somehow Cohen said, well, if you just pick a random, I think he was really thinking he was a probability theorist. If you just randomly make all these choices, it will automatically give you the right thing. It's
okay.
I mean, there's this. Do you know much about what is it called? The Rado graph? How do you pronounce that name? It's like the generic graph that you get when you just start randomly generating graphs by you have a bunch of vertexes and just sort of randomly adding edges and some protocol. I forget exactly how it works, but right, there's what?
Yeah, there's this infinite graph. Well, let's see. I mean, now you make me think of Erdős-Renyi graphs where you add edges with probability p. But I think
there must be a lot of Erdős stuff lurking around here, but I don't know exactly how he fits into the theory. Except that.
But anyway.
Yes.
Yeah, but anyway, there's this generic countably infinite graph that contains all finite graphs and has other cool properties.
Yeah. So the very rough idea here is that when you take the double negation topology, and by the way, one of the things you should really think about here is what is it? The double negation. Right. I mean, there's the double negation topology in topos theory, but there was originally the double negation topology in just ordinary point set topology. And it's very fun to think about what it is there. And it's connected to all this story about the radograph and everything like that, and generic things, and things that happen with probability one. And I'm way oversimplifying the story, but if you take the category of set valued functors on a category, then very roughly speaking, you're expecting to get the topos whose model category is that category. that's the way I just stated that is that is only true for ridiculously simple site categories, or maybe I should call this the cosite category, because we're not taking the pre-sheaves on the cosite category, but we're taking the set-valued functors on the. So there's just this issue of what's the variance of the things here, but so in general, what happens is you get the theory of not necessarily objects in the original category that you started out with, but also some kind of infinite limits of them. And yeah, right, this is the content of Diaconescu's theorem. And okay, so what happens if you take the topos of set-valued functors on some reasonable category? Probably let's say a small category. Maybe it's going to be even a finite category. I'm not quite sure, but let's just say a small category for now. Take set-valued functors on a small category, and you take the double negation topology of that. And that gives you something which I can roughly describe in this way. So, and right, and this really is related in some strange way to Lever's philosophy of Hegelian dialectics and everything like that. How
we're in enough trouble already.
No, we're not. So the idea is that a morphism in a category is supposed to be sort of like a progressive improvement from a certain point of view. This is like, I don't know, this has something to do with dialectics or something like that. And groupoids are sort of these categories where you don't have this dialectic improvement going on. So everything's just static. I mean, who is it, right? What is this ancient argument between these two guys? Heraclitus.
Well, Heraclitus was the float. Parmenides is the name of it.
Parmenides, yes. Yeah. So I don't think it's. I'm sure I heard Lever talk about this, but don't accuse him of believing in my crude retellings of this. So in some sense, it's Parmenides is to groupoids as Heraclitus is to categories, and Heraclitus categories have to do with these. I'm not sure improvements is exactly the right word, but progressive development or something like that. And so in Cohen's philosophy of all of this, right, you sort of want all the progressive developments to occur. You don't just want some of them to occur. You want all of them to occur, and you somehow want them to magically occur in a way that they don't interfere with each other. And the double negation topology is this magic thing that accomplishes this in the context of category theory, in the context of the doctrine of geometric theories. So in other words, what I'm saying is that if you have a non-invertible morphism in your
site
cosite, right, in your site category. I think it is the cosite. The cosite is like the models, whereas the site is like the spaces in some sense. So if and you can think of it either way, but it's just that there's an asymmetry between domain and codomain here, and it gets reversed depending on whether you think of site or cosite. So it's like the double negation topology gets rid of the old things. It gets rid of the models that aren't new and improved. So, you have like F sub P, and there's this non-invertible morphism from F P sub P to F sub P squared. And that means that F sub P squared is better. So it's like, F sub P does not occur as a model of the double negation theory. Because it is, in some sense, ruled out by this progressive improvement process.
That's cool.
And by the way, it's a great thing to do to really understand this story. I'm presenting in this ridiculous way, but to really understand the details of this story is a great thing to understand. But that's not.
Can I ask an example question? I don't know if you know.
Yeah, go ahead.
You might know this example. So, like, suppose we started out with well, there's this op that's confusing me, but also it's like pre-sheaves on the post set of natural numbers. But maybe I mean actually co-pre-sheaves on that. So like a set for each natural number, and then maps from the nth set to the n plus first set, going on forever. So no one of them. So all these morphisms are these sort of things you're talking about.
This is a great question. And
so then when you do the
so
double
horrible
negation,
that I can't give you a great answer right at the moment. We should really do this for homework. And it's really going to depend, as you say, which direction you're doing it, the co-sheaves or the sheaves or something like that.
I'd hoped you'd know this one, because this is sort of some basic one where, like, so it sounds like when you're done, you get like the category of
you get category steps. Yeah, in other words, you get yeah, I mean, right. In some sense, I think you're talking about taking the 1-point compactification of something or other. Let's see. It's. I mean, this is such a great question, but
I was thinking you might get.
But I think I'll screw it up if I try to do it. I mean, we should really return to this question. Yeah. What? Say it again. Yeah.
For some reason, I was thinking you'd get something like category of sets with an automorphism. I was thinking that this step forward in time would get turned into.
That's a very interesting idea. I'll have to think about that.
But you're saying that maybe
it's hinting at scaling deformations or something like that.
Well, no, but I was thinking that you keep in these morphisms, but they become invertible. But maybe they just maybe you're just saying, like, you throw out all the finite natural numbers because each one of them is smaller than something else, and you're just left with this infinity or something like that. So you get just this one.
Well, but it sounds like you're talking about post-settle site categories.
Yeah, that's true.
I don't think you can leave the realm of post-settle things by this method.
Okay.
So you need something a little bit fancier that's less post-settle in order to get something that's going to have some. But can I try? Let me try to give you some other stupid examples, which I think are correct when you do them right, but I'm not sure I'm saying them correct. I want to say something like, there's a certain version, right? When you talk about the category of graphs, there's a whole bunch of fine print involved in what's your exact definition of graph and what's your exact definition of morphism between graphs. But if you do it the right way, then you talk about the category of finite graphs. And you can take the set valued functors on that. And then you can
graphs, you mean something like graph theorists' graphs as opposed to quivers?
Yes, but I think what happens is I think they don't have multiple edges. I think it's
that's the graph theorist graph,
Yeah, I think that's right.
Okay.
And you put in the right kind of morphisms, you take the double negation topology on this set valued functor category. And I want to say something like you end up with the torsors of the automorphism group of the Rado graph or something like that.
Oh, wow. Okay. Okay. So there's somehow the endomorphism.
Yeah, it would be the theory of a Rado graph or something like that. But again, there's a lot of fine print involved in getting that to work correctly. I'm not sure what's his name could tell us. Michael Schulman could tell us the answer right off the top of his head. But what were you going to say?
So there, it's like the automorphisms of the individual finite graphs are all sort of getting built into the automorphism group of this Rado graph. I mean,
yeah, and I think the first way I stated it was that it's the torsors of this group, but the other way to state it is that it just is the theory of a Rado graph. And again, the Rado graphs have lots of automorphisms. So I'm hoping that example is somewhere close to correct, and that it's actually a good illustrative example, although it's also in a way a very sophisticated example. But the good unsophisticated example is this example that we're talking about here with the finite fields, and we just get the profinite completion of Z, or something like that.
Yeah,
right. We're saying it's like the theory of an ideal finite field, and these ideal finite fields include some sort of direct limits of finite fields or something like that. But then when we take the double negation topology, we're saying, no, you're not allowed to stop at any finite stage. You have to keep on going forever. And I think that means that you end up getting, this theory of an algebraic closure of F sub P. But you can restate that as being a torsor of this, absolute Galois group, which is just this profinite group, the automorphism group of the algebraic closure. And as you say, it's very group-like because of the double negation aspect that's connected in a very direct way, as you pointed out a long time ago in the discussion. And right, we're saying that there's right, and this double negation topology, it's just a full subcategory of this slice topos that we were talking about. So we're saying that what is this topos that corresponds to this profinite group? Well, it's just this thing that we've been talking about in recent months. Don't tell me, it's the don't tell me, what am I saying? Is it like the finite actions, or I maybe call it the continuous actions of this profinite group? But I think you could also describe it as being something like the actions, maybe with the property where each orbit is a finite orbit. So maybe is that all it is? It's just actions of Z. So is that right? Something like that. So we're saying that these Dirichlet types, there's a Grothendieck topos of Dirichlet types that are this, the double negation topology of this slice topos of things over the Euler summand of the logarithm of the Riemann Zeta type. And you know what I'm saying? We're saying there were some really good reasons there, some really good conceptual reasons ultimately why these Zeta types are related to the algebraic, are related to the arithmetic geometry of commutative rings, and even more general than commutative rings, algebraic stacks and everything like that. So
I didn't get that last.
Okay. So I'm just trying to say some big picture stuff here. That I'm trying to draw some nice connections here between the thing we started out way near the beginning today, where we said start out with a community. Like maybe I can find it here. The you start with a commutative ring A. You get this zeta type from it, and it has to do with harming the commutative ring A into finite fields. And that's a zeta type, and it's, you know, it's if you think about it, it's, if you do it in the right way, it's in one of these slice toposes, or it's the exponential of the thing that's in this slice topos, or something like that. And right, I mean, these zeta types, we know that these are conceptually nice categorifications of these analytic objects that have this storied history in tying together algebraic geometry and number theory and analysis and everything. And I'm saying that if you really investigate all these stories that I'm trying to tell you today, then there's really good conceptual reasons why all this is happening. That this zeta type of a commutative ring, for example, but even way more generally, this zeta type of an algebraic stack or something like that, is going to fit into this story about the double negation topology and everything. So, I mean, right, there's going to be there's going to be I mean, right. So, right, we said that this topos of continuous actions of the profinite absolute Galois group. So, I mean, that's a topos, you know, so it's a theory. But think about what that means in terms of the theory, the syntactic category of the theory, right? What are the objects of the syntactic category of a theory? Morally, they are the constructions of the theory, the things that you can build in the theory if you have a model of the theory. So what we're saying is that, you know, in this theory of an algebraic closure of F sub P, what are the constructions that you can have in there? And among the very important constructions that you can have are these things that you get by harming the commutative ring A. Any commutative ring A, or any, you know, it could be an algebraic stack or something like that. But let's say, for example, a commutative ring A, but by harming that commutative ring A into all the finite fields of characteristic P. Or you can even just think of it as just harming them into the algebraic closure. Just harming A into the algebraic closure. And when you do that, you get this thing, right, that is acted on by the absolute Galois group. And so it's this, it's in this double negation topology. It's in this double negation topos. It's in this topos of continuous actions of this profinite absolute Galois group. And
is this, can I?
Yeah, go ahead. Yeah.
So could this be some kind of explanation for why people get L functions from Galois representations?
Absolutely, absolutely. That was my very next punchline that I had totally forgotten to say, and I wouldn't have remembered to say if you hadn't just reminded me. Yes, that's right. I mean, you might, again, if you think about you and me trying to figure these things out decades ago, that question you just brought up was one of the things that I don't think we ever really figured out, or I was really confused about, at least. And I don't know if to what extent my confusion spread over to you. But, you know, we had this whole theory of these categorified zeta series. And when I very naively tried to extend that to categorification of L series, it really didn't work very well. Whereas now, with this story that I'm telling you now, it really should work very nicely. And so one thing about these categorified L series is that all the more so compared to the Zeta series case is you really do probably want to, you know, focus on one prime at a time to a great extent. You know, you really want to understand L series, all the more so compared to Zeta series, in terms of their Euler factors. And, you know, and then you realize that there's this Frobenius action at each particular prime. And so you're dealing with, yeah, I don't understand everything here, but yeah, I just want to say that yeah, you're really on the right track there. You must be. I mean, I don't understand enough to tell you how you're on the right track, but yes, you're on the right track.
That seems like lots of fun to dig into.
Right. So, okay, so now I got a pretty short amount of time left, and that is just barely enough time, hopefully, to tell you about how we're planning to try to apply all this to the concrete problems that I've been thinking about trying to classify Z mod 3 torsors over finite fields. So in other words, in some sense, so it sounds like what I'm saying is that I want to study the zeta type of a certain algebraic stack, and that is the algebraic stack of Z mod 3 torsors. So, you know, we have to try to get everything to parse there. And I do have some troubles in trying to get this all to parse. I'm confused by things that are happening, but, you know, it's all stuff we can try to work out here. So, let me, sorry, just still struggling with this thing here. That's not quite right. How does this work? Okay. So what am I trying to say? So, all right, and we really are aiming for 10 a.m. quitting time, right?
Sounds good to me. Yeah, I should.
Okay. So, you know, except I wouldn't mind how about a 5-minute break now and then 10 minutes?
Okay.
Okay, I'll be back, okay? I just want to go to that. Okay.
Now it's going. Okay, it's just super slow today.
Oh, okay. So, yeah, as I was thinking this over, it really does seem like, you know, this whole thing about where Lovier interpreted Scott-Solovay forcing in terms of, well, or Scott-Solovay interpreted co-enforcing in terms of the double negation topology or something like that. Right. It's like, I mean, it's a beautiful thing, but in a way it's right. It's Lovier, right? I mean, Lovier loves the dialectic progression. But the double negation topology is like freezing that progression. It's going over into the Parmenidean domain or something like that. So in a way, it's, you know, I can imagine Lovier being unhappy about that, and maybe thinking that, you know, actually you shouldn't just throw everything away by going to the double negation topology. You should study a lot of things without going to the double negation topology. I don't know. I don't know exactly how Lovier would think.
Oh, he wasn't. Yeah, I mean, he was not the world's biggest fan of classical logic, so he might be very interested in studying how you classicize something, even if it's destructive.
And again, he was or wasn't into. What did you say again? Just repeat again.
He was. I thought he was into intuitionistic logic, and
I'm not sure intuitionistic is the right thing to describe that. You know, he was into geometric logic.
Okay, whatever. But anyway,
but it's right. It's related in some
don't have the
way to intuitionistic logic.
I get curious about. I can imagine being interested in what happens when you force the excluded middle on things.
Sure. And
as long as you don't have to, it's fun to study what you can.
Right. Yes, I think that's exactly right. Yes. But okay. So now what am I trying to say here? So yeah, so there is this. So, okay, now we are back, right? We have this funny interplay between doctrines. So now we're back in the doctrine of algebraic geometric theories, not geometric theories, but algebraic geometric theories. So this is not Grothendieck toposes. This is, our usual two rigs or whatever.
Uh-huh.
And we've got T is the theory of a Z mod 3 torsion. Boy, there's so many tricky things going on. It's the theory of a Z mod 3. So what is that? What is that concretely going to be? Well, depending on how you parse it, it could be a couple of different things. Let's say that we're like working over the rationals for a moment. And we may have to change it to working over the integers instead of working over the rationals, but I'm not quite sure yet. But either way, you would take the representations of Z mod 3. Representations over, whatever this base field is, or base ring that we're talking about. So perhaps over Q or over Z or whatever. And you can see that this is already, right? This is already hinting at something about your question about, how L series and Galois representations enter into here. Because, right, somehow we're switching between the topos thing, which was the set valued representations, and now here we have vector space valued representations.
Uh-huh.
So there is something going on there. I hope I didn't make too many horrible level slips when I just said that. Yes, so this is going to be a thing to which we should be able to talk. We should be able to take the zeta type of this, except that since this is, this should be seriously stacky. So we shouldn't just expect this to be a zeta structure type. I'm confused about what's going to happen here, but I'm somewhat anticipating there's going to be a zeta stuff type. When I actually tried to calculate it, I actually didn't get that it was a stuff type, but I think it is going to be a zeta stuff type.
So can you tell me what a zeta stuff type is, especially because now we're in this other doctrine.
Sure. So right, there are also, for Joyal structure types, there are various ways of thinking of it, right? You can think of it as a functor from finite sets to set or something like that. But you can also think of that as like a discrete vibration over.
I'm
saying this right? Is it?
Yep. Just let people know you mean the groupoid of finite sets, I guess, and the category of sets. Yeah.
Okay. Yep. Yeah. That Bij is supposed to stand for bijections as the morphisms. Yep. And then so you have F, and then you have like this thing that corresponds to F that's like, I don't know, points of F or something like that. I'll just call it F hat for the moment.
Yep.
And you can go back and forth between these things and here. So, okay, so a stuff type would be, it would be like, it would be just like groupoids over here. And it would correspond to some kind of vibration over here, but I might have to think about what kind of vibration. It would be like a split vibration or a cleft vibration or something like that. But maybe you should just think of it this way. But let's see, if you think of it this way, then you might have to think of it as a Pseudo-functor. Yeah, maybe that would make a difference.
Right.
It's something like that. But
Yep.
so it's going to be something like that. It's going to be something like that.
Yep.
And so that's the idea. That's the idea, that we're going to try to take the zeta stuff type or zeta structure type or whatever it is, the zeta stuff type of this algebraic stack, the stack of Z mod 3 torsors. And so, we're going to get Z mod 3 torsors over finite field. And again, not just over finite fields, but over their algebraic completions. And algebraic closures, whatever they're called. And the last punchline I'm trying to deliver before we wrap it up is I don't understand this yet, but I think something interesting is going to happen. It's because what am I trying to say? It's from one point of view, it's going to be very trivial to classify the Z mod 3 torsors over a finite field. I think that's sort of the Frobenius point of view. You just give the Frobenius monodromy or whatever you call it of the torsor, and it's just like an element of Z mod 3, because it's like a homomorphism from this algebra geometric fundamental group, which is this generated by the Frobenius, into Z mod 3. So it's just like picking out an element of Z mod 3, because the profinite Z is close enough to Z when you're homing into Z mod 3. So,
okay, well, there are not many of those.
Right. But then you also have to worry about what are the morphisms between torsors and stuff like that. But it should have a very simple classification. It should just be you just give the elements of Z mod 3. But there should be another way, another more explicit way to classify the Z mod 3 torsors over finite fields. And that's where you actually give the torsors very concretely. So you say that, it's going to be like the cube roots of this element in the finite field tensored with the Eisenstein integers. There's going to be some very explicit description of the torsor. You can think of it as a very specific Frobenius algebra or something like that. Is that what we call them? Frobenius algebra. So separable, yeah. And once again, right, the suspicion that Frobenius only did one thing in his life keeps on showing up here, because somehow we're tying together the Frobenius with the Frobenius algebra and everything.
Yeah.
That could sound bad when you say he only did one thing in his life, but actually it's better because he unified all the things that he was doing in his life. So the idea here is it's not that this is going to be a difficult classification problem. Again, according to the Conway philosophy, we're going to a ridiculously easy problem. But what's going to happen is that there's going to be two ways of classifying the Z mod 3 torsors. One just by giving the Frobenius monodromy, the other one by giving a very explicit description of the torsor. And we're going to explicitly work out the connection between those two pictures. And that's going to hopefully be very easy. I admit I'm already getting myself confused by it, but hopefully going to be very easy and nice. And then we're going to try to glorify that back into the original problem of understanding the Z mod 3 torsors over the number fields instead of over the finite fields. So we're going to have this correspondence between Frobenius monodromy and explicit torsors in the finite field case. That's our local thing, and we're going to sort of try to glorify it into this global thing that's going to be the same correspondence in a way, but just glorified and globalized. And that's the project. So thanks a lot for listening.
Thanks. Okay, yeah, well, I want to hear a bunch more details about that last stuff because that's sort of getting us back to where we had been.
Yes, yes, yes. But you know, in retrospect, I'm not surprised it worked out this way. That I've now just prepared us, hopefully, for actually going ahead and starting to do this next time. That's my plan.
Okie doke.
Okay. Thanks a
Okay.
lot. Okay.
Yep. See you next week.
Okay. Bye.